I'm Neil Cornish. I'm going to cover a few different things. The next couple of days, I'll be talking mostly about the LISA mission. I thought I'd just go over a few things in gravitational wave parameter estimation. Teja covered a bunch last week, but I'll just touch on a few other things. This looks like a really great program. I've had the pleasure of lecturing at quite a few different summer and winter schools over the years. Cargès in Corsica, Les Ouches in the French Alps, Saas-Fee in Switzerland in the Alps, and Atrani on the Amalfi Coast, and now Princeton, New Jersey. It's and this is the nicest bit of New Jersey, but I don't see mountains or beaches. It's a bit of a downgrade other than that, but you know, it is very nice. It is very nice here at the Institute. So, okay, well, all right. So, outline for today. I'm just going to talk a little bit about the likelihood function, which I know was covered last week, but just revisit that a little bit. Get a little bit into the machinery of how we do this Bayesian inference and how we're extracting information from the gravitational wave data. And in particular, I'm going to talk a bit about transdimensional inference, which is one of the specialities of my group. And like I said, a lot of this was covered last week, but I'm going to revisit some of it, maybe with a slightly different spin. So it's actually cool to go back and look at the history of where a lot of the techniques we currently use came from. I actually wrote a little for every LIGO paper, there's a public like explainer, 2 pages or something written. So I wrote a little one for the paper, the guide to LIGO-Virgo data analysis, got into the history a bit of Gauss and Laplace, about how all this came about, and really the methods we're using are very much based on their original works from 1800s. And I mean, Laplace essentially developed all of Bayesian inference, and then Gauss introduced things like the normal distribution, and that then led to understanding of it in the context of the central limit theorem. And basically the idea that Gauss had was if you had data and you had a model, if you just subtract the model from the data, what you should be left behind is noise. So that's really all it is that we're doing. But of course, that means you need a model for both your signals and you need a model for your noise. Because if you're saying, I'm going to subtract my noise off, sorry, my signal off, my model off, until I get down to noise, well, if you don't know what your noise is, how do you know that you've actually done the subtraction correctly, right? So I think that over the years, most of the work in gravitational waves, people have always focused on the signals and less on the noise. But as you see in the context of things like pulsar timing, the noise is really important, and it changes your astrophysical results if you don't model your noise correctly. So talk a little bit about the modeling of the noise. Okay, so Gauss proposed the model that the noise would be represented by a normal distribution, and then if they were independent per bin, then you just get the product of all of those different bins. And so this would just be this was the chi-squared that Gauss first introduced. And then if you go beyond that, you can actually have correlations, say, between different samples. Then what you want is your residuals, your data minus your model here. So D is the data, H is your gravitational wave model in our case. And then you have the noise correlation matrix. The case I was just giving you before was for stationary white noise, where that correlation matrix is just a diagonal matrix with diagonal entries being the variances. And the chi-squared, as I mentioned, is just the chi-squared goodness of fit that Gauss first introduced. The problem with this, if you had a more general noise correlation matrix, is that this matrix inversion for a completely general matrix scales as the number of data points cubed, which can get quite expensive. And even after you've got the inverse, actually each likelihood evaluation, assuming you weren't updating your noise model, is still n squared, right? And that's the problem we really run into in the case of pulsar timing, because we actually have to work there with a time domain likelihood function. And so we have to do the inversion, and we have to do these sums. And clever tricks have been developed to cut down this cost quite a bit. but it still is essentially an n cubed, n squared type problem there. That's why the evaluations of the likelihood in the case of like pulsar timing are much more expensive for, than they are for LIGO. And as the number of data points grows, as we get more pulsars and more years of observations, that really becomes a challenge. So a common assumption made certainly in the LIGO analyses, totally not in pulsar timing, is that the noise are stationary. So it means that the expectation value of the noise process is constant, as is the expectation value of the products, and it only depends on the lag, right? So it doesn't depend on the particular time. It just depends on the time difference between your two samples. And so you've got this correlation only depends on the lag. And the nice properties that this have, it then means that it's actually can be represented as a circulant matrix. And we have that if you take this limit and the long time limit of this expectation value, that you actually get the power spectral density. And here's in the Fourier transform. And as Tejo went through last week, in practice, we only have finite observation times. So the Fourier transform wouldn't necessarily formally exist. But we usually use various window functions, but those then introduce various, they say destroy stationarity, for example. So we're always working with some degree of approximation in our likelihood functions. The reason that LIGO analyses, LIGO-Virgo, now I guess CAGRA analyses are all done in the frequency domain is the Wiener-Khinchin theorem says that the power spectral density of wide sense stationary process, so this is noise that where the variance and the mean don't change with time, is just given by the Fourier transform of the time domain correlation function. And so that ends up, if you've got finitely sampled stationary time domain data, your noise correlation matrix is then diagonal in the Fourier domain. And it's much easier to invert diagonal matrices, right? Because the cost goes as n, not n cubed. And then the evaluation of the likelihood also scales as n, right? So it's a circulant matrix if it was stationary and periodic, and then you can diagonalize it by a Fourier transform. So a Fourier transform diagonalizes that's the noise correlation matrix in the Fourier domain, and that's in the time domain. Now, as I mentioned, if you apply a window function, you actually destroy stationarity, and then the noise covariance matrix is only approximately diagonal, so you can introduce some amount of error in your analysis if you've got window functions, but it's usually a small error. So switching to the Fourier domain, the expectation value of your noise process now, it's uncorrelated between frequency bins, so you get this delta function, and in the discrete case, it goes across to this. So I think this was all covered last week, but just wanted to do that again in my notation. So in the Fourier domain, this noise weighted inner product looks like this, which is the familiar expression you'd see in all of the LIGO-Virgo type papers. And when we talk about whitening data, it means that we take the data and we divide by the amplitude spectral density, so the square root of the power spectral density. And then the basic idea is you have the data, you have the signal, you subtract the signal from the data, and you're left with noise. This actually is GW150914, band passed and whitened. So you clearly see the signal sticking out, you subtract. The reason the signal is all jiggity, even though the numerical relativity template was nice and smooth, is we've whitened it, right? And so all of these features come from the whitening process. In fact, mostly from the various spectral lines in the LIGO spectrum, put in all these wiggly bits, because you lose Fourier components from your model then. Anyway, so this is the basic idea behind the data analysis. going back to Gauss, data minus signal is noise. Now, the problem is the LIGO data, LIGO-Virgo data are not stationary, and they're not Gaussian. In general, we have periods of time where we might have an elevated noise level, and that's over long periods of time. And then you can also have more impulsive noise transients like glitches. And we covered this in this paper, the Guide to LIGO-Virgo Detector Noise, which has this archive link. So in reality, we have these kinds of issues to deal with. And also, even if the data were perfectly stationary, once we apply our window functions, it takes it from a diagonal covariance matrix to something with off-diagonal terms, right? So the diagonal nature is broken. Okay. You could always find there's always going to be a basis where the noise covariance matrix is diagonal. The problem is, a couple of problems with that, and the theorem's correct, but there's a couple of problems with it. One is the cost of finding that basis can be very high. And even if you found it, it only works for one stretch of data. And then you can't really interpret it either because you don't actually understand that basis like we understand, say, a Fourier basis, right? So it becomes difficult to understand. So yes, in principle, you could always find a transformation that gets you into a diagonal noise covariance matrix, but it's going to be hard to interpret and costly to actually find that basis. So you might be better off like what we do in nanograv, just sticking with, say, the time domain basis and then just dealing with taking the inverses. And again, just repeating what I said before, if it happened to be wide sense stationary, so long term, the variance and the mean don't change with time, then you get the nice diagonal structure. So as I was mentioning, the actual LIGO data, and again, this is taken from our paper on the LIGO-Virgo Guide to LIGO-Virgo Data Analysis. It's a really good paper just to look at as just a general introduction. And you see that if you actually look at the spectra, this was, I think, from the Hanford instrument taken at these different GPS times, each about a minute apart. I think 4 seconds of data each a minute apart. We picked for the paper, we picked some bad data, right? Like where the instrument was bouncing around a bit, just to really emphasize the fact that the power spectral densities do vary with time. So it's not normally quite this bad, but just out of illustration, we showed that for these particular times, you get these really big variations in the power spectral density. So in addition to this variation, which is usually a bit more subtle than this, we also have these noise transients. So this isn't a time frequency representation. This is what we call a glitch. And in this case, the glitch was lying on a track of a signal, this particular signal here. And so we then go ahead and subtract these glitches out, preferably jointly with the analysis. So you were taking out the noise transients. Once you take out the noise transients, the data are pretty consistent with being normally distributed. But the noise transients make it quite non-Gaussian. So one of the things that I've been working on quite a bit recently is models for non-stationary noise. And for example, the LISA analysis we now have formulated in this fashion. So we use a discrete wavelet basis. And in that basis, here's the definition. So this is locally stationary noise, is noise that is sort of adiabatically varying in time in its mean and variance, right? So it's not dramatic. This doesn't cover glitches. That's impulsive sort of changes. These are sort of the slower drifts we see over time. And so it's formally defined in this paper what we mean by locally stationary noise. And then you can prove that there are various wavelet bases that maintain a diagonal structure in their noise covariance matrix for locally stationary noise. So you can get the advantages of, being able to find the inverse to a diagonal matrix if you use this model. I mean, of course, the noise might not be perfectly described by locally stationary. It's a better approximation than saying it's stationary. We know in the case of, and I'm going to talk more in the next couple of days about the LISA detector, with LISA and even with the next generation ground-based detectors, we will have signals, say, in the ground-based detectors, say, from a binary neutron star merger, that will actually be detectable in band, right? So within the sensitive range of the detector's frequency range, that will last for like a day. So unless they manage to, miraculously change the way these detectors work, it's hard to imagine that the detectors are going to have a constant noise level over a day. I mean, the current detectors, it varies quite significantly over minute-type timescales, right? So you're probably going to want this for the next generation ground-based detectors to account for the stationarity. There are different ways. You don't have to use a wavelet basis. And certainly for LISA, where many of the signals are going to be detectable for years, it's hard to imagine that the detector noise is going to be just constant for years at a time, right? And even if the detectors were perfect and the noise levels did not vary, we know that there are going to be unresolved signals. There are millions of white dwarf binaries in our galaxy. We're only going to be able to individually resolve tens of thousands of those, so there's still going to be millions left. And as the detector orbits, its antenna pattern is sweeping across the galaxy, so you get this modulated noise, essentially, from the unresolved galactic binary. So that's non-stationary for sure. So you have to do something about the non-stationarity. Wavelets are one approach to doing that. So here, instead of having a power spectral density, just S of F, it now becomes S of F and T, right? So a dynamic spectrum that depends both on frequency and time. Here was some kind of an autoregressive moving average model that I simulated with increased variance at this point and then down again, and there's its dynamic spectrum. One of the cool things about using time frequency is that each harmonic of a gravitational wave signal just traces out a line in time frequency space, and there's root n. If you've got n data points, there's root n data points in time, root n in frequency, and any line in that space has length root n as well. So the computational cost of calculating the likelihood is some prefactor times root n. That prefactor is a little bit of spread around the line, and also if you have multiple harmonics, you've got to do it for each harmonic. But the scaling goes like the square root of the number of data points. I think Teja mentioned yesterday one of the techniques used in if you're doing a purely Fourier domain analysis using techniques like heterodyning, or also known as relative binning, to cut down on the cost of the evaluations. You get a natural heterodyning because you only evaluate the likelihood along the signal tracks in the time frequency. And what we've been testing recently in our in our LISA analyses, our waveform models in the wavelet domain, previously the codes that we're working on were fully in the Fourier domain, and they used heterodyning for likelihoods. Now we've gone to the wavelet domain and we're just evaluating them along the tracks. They're a little bit slower, factor of 2 or 3 slower than heterodyning, right? But not much different. And the nice thing is you don't need a reference waveform like you do for heterodyning. So because they're always just along tracks, so you don't have to carry around a reference waveform to heterodyne the signal with. So it's not quite as fast, but close, and a bit simpler to implement. Okay, so some of the challenges we have to deal with in gravitational wave data analysis, an individual signal, such as an extreme mass ratio in spiral, two black holes on eccentric orbits, both with spin, that's described by 17 parameters for that one signal, right? So you got in that case, a 17-dimensional parameter space. And then when you go to future detectors like the ground-based instruments and also LISA, you'll have many signals in the data at once. So it's 17 parameters times some large number of signals. You have to jointly estimate your noise properties along with the signals. You can't just, especially when the signals are persistent, you don't have noise-free data that you can try and learn the noise properties in. You have to estimate it with the signals. And you also have, and I had a little animation that stopped blinking now. This was the GW170817, the first binary neutron star merger, was the thumping great glitch in the Livingston detector. I'll just back up and go forward again if I can. And so we actually subtracted that glitch. And this is actually the subtraction done using Bayes wave, an analysis technique that my group has developed. So we subtracted this glitch. It was actually the first event that we actually ever, we'd pitched this to the collaboration that we would subtract the glitches. And they're like, no, we don't want to do that. And then this neutron star signal came in, and there was this big glitch. They said, maybe you could subtract that glitch now. Because they were worried that if we were subtracting glitches, we might impact the analysis of the gravitational wave signals, right? So they thought it was dangerous to do that. But then the best ever signal that we had, of a binary neutron star comes in with a giant great glitch on top of it. So we subtracted off the glitch and sent them back the clean frames, and they analyzed those, yeah. The cost? Oh, the cause. I think this one's kind of silly in a way. I think this was like a digital overflow error, if I remember. Like it wasn't even like something purely mechanical. It was something in the readout system, which is annoying when it's, it wasn't like a bit of stuff falling through the laser beam or something. I'm pretty sure this was an overflow in one of the readouts. And they happen. Big glitches like this happen every few minutes. So, and actually, as the LIGO detectors, you've seen those plots where they showed the LIGO sensitivity in the first observing run, or even going back to the initial LIGO, and you see that steady progression, right, where they've just brought down the overall noise level. The problem is, at every iteration, the number of glitches has got higher. I think it's just like you expose more, once you get the sort of like baseline lower, you just expose more of the little pops and crackles, right? So they've actually, overall, the data's glitchier than it used to be, or at least now we can see the glitches that before were just hidden under the level. So, so we do a lot of this glitch subtraction stuff. Yeah, so what we are looking for is, in the Bayesian approach, we're looking for the posterior distribution. So this is the probability of seeing a particular waveform given the data. And you've got your likelihood, which I was just talking about, which is your noise model. Then you've got your prior, which is your signal model. And then you've got your normalization factor, which is the model evidence, which becomes very important if you want to compare one model to another. I like this quote from Laplace: the Bayesian theory of probabilities is basically just common sense reduced to calculus. It probably sounded better in French, but Linley's today's posterior is tomorrow's prior, right? So there's this idea of updating, right? You go from what you currently know, you have new data come in, and you update that to your new state of knowledge. And you can actually measure how much you learn by using the KL divergence between the posterior and the prior. And in bits, this actually measures the number of bits of information you learned from the data, right? So if you do an experiment and your posterior looks identical to your prior, you haven't learned anything. Whereas if your prior was very broad, you do the experiment, you end up with a very tightly peaked posterior, then you've learned a lot, right? And it's measured by this. So it's a learning process, basically the scientific method turned into computations. And if you have, I was suppressing the index, sorry, I was suppressing the label of also always having to operate under a model. But you can also have the probability of a model given the data. And so that's the product of the prior probability of that model times the evidence for that model. So that evidence was the denominator in what I was showing earlier. And then you can have your odds ratio. So it's your prior odds ratio. So for example, you might be comparing general relativity to an alternative theory of gravity. So you might have some prior odds saying, I really think that GR is probably right. And this alternative theory is kind of wacky. So it might not have a very, and then you've got the Bayes factor, which is the ratio of the evidence then given the data. So you have to kind of overcome whatever prejudice you might have against a theory to begin with. And if you have enough data that's informative, you can then overwhelm that with the Bayes factor. And we can talk about how to compute Bayes factors. Right, so that's the, again, Bayes theorem. There's the evidence, which involves doing this integral. And so there's a variety of different techniques to perform these computations. I'll talk a little bit about Markov chain Monte Carlo techniques. And that allows you to sample from this distribution without actually even needing to compute the evidence. You have to kind of go back and compute the evidence later. And then there's other techniques such as nested sampling, which give you they primarily give you the evidence, but you can also get the posterior distributions. So there's very different sampling techniques that are used. And these days, I think you heard about it a bit last week, there's now all of these simulation-based inference techniques that are being introduced as well, with a more machine learning kind of bent to them. And they have their advantages and disadvantages. So the priors on your gravitational wave signal are your models. So the strongest prior you can have is a template-based analysis, which says the data is given by some model parameterized by some collection of parameters. Those parameters might be the mass and the spin of the black holes, where it is on the sky, right? And that's a delta function prior that says that it's just given by this template. You can also model directly the gravitational wave as, say, a sum of like wavelets. That's what we use in Bayes wave, and you have some kind of priors on what wavelets you want to use. And then for stochastic signals, the prior is that they're actually coming from some kind of a probability distribution, and then which is described by some correlation matrix, and you might have priors on that correlation matrix. For example, it might be a power law if you're doing, one of the popular models used in modeling stochastic backgrounds. So these are all just different priors, and so that's all it is. It's all exactly the same likelihood, and then these are the different priors that we use for different kinds of analyses. So, yep. Yeah, so supernova, we don't have really good templates for those, right? I think there's a supernova waveform here. I don't know if this one's a made-up thing or whether it's a supernova waveform. But people do numerical simulations of supernova. They also do numerical simulations of, say, neutron star mergers, right? The final merger after they've actually contacted. But there's all sorts of messy, there's neutrinos and there's nuclear physics happening and all sorts of, dynamics there. That means that we wouldn't use those as templates because they're not, they might capture a fair bit of the physics, but they're not going to be something that you can actually parameterize easily and then just model those few parameters. So we tend to use more like the burst type techniques, like measuring them as, modeling them as a collection of wavelets or something like that, right? Because we don't really trust those simulations to actually produce a template that we could use. But we do have, for gravitational wave, in spirals, we have good templates there from both post-Newtonian theory and numerical relativity. Of course, then we got stochastic signals, either from a population of large number of astrophysical signals or perhaps something in the early universe, like a phase transition. So we have all these different kinds of models, and we just use those all with the same likelihood. So these are our models, and then how we use them. So in the case of just directly modeling something you do for supernova, but it also works for black hole mergers, is in the case of Bayes wave, what we do is we just model a signal as a collection of wavelets. And I'll talk a bit more about this later. It's a trans-dimensional code, so we don't tell it how many wavelets to use. So both the number of wavelets and the parameters of those wavelets, these are continuous wavelets, so they each has 5 parameters. In addition, you can have the sky location of the source, that sort of thing. So here's an example where just a single draw from Bayes wave. Here are each one of these color-coded, these are each different wavelets. These are, in particular, Morley-Gabor wavelets. You add them all together and you get the signal. And here's an example from the very first gravitational wave detection. And this was our reconstruction that we did using Bayes wave. And we did this on the day that the data came in, and it was before we had any of the template-based analyses had finished running. So it was discovered by a burst analysis. So CWB picked this up because the template-based analysis for high mass systems wasn't running at the time. So it was actually detected by CWB, and we reconstructed it with Bayes wave that day, and this is what we got. And it was pretty exciting because it looked just like the things that Franz Pretorius had been publishing about, back in 2005 and 6 of like what, and then people did much more after that. But this looked like a lot like what a black hole merger, and there was nothing in this model that told it to be a black hole merger, right? So it was neat to actually just see coming straight out of the data. Now we were lucky here. This was a relatively loud, relatively high mass signal, which is well captured by a small number of wavelets. If you feed in a binary neutron star at moderate SNR, we don't pick it up with this model, right? So wavelets have their uses and but this is a very general, this model is not very, well, I should say it's very general, whereas a template-based model is very specific. So you can dig a lot deeper into the noise with a model, but you can't discover new things with a template, right? This allows us to discover new things.
What makes sure?
Yeah.
What makes sure that the new things that you're actually detecting are real things? Because in template matching, you know
right.
What are the templates.
Yeah. You want multiple detectors. The more, the better. So in one detector, you would never believe that you detected a gravitational wave signal with this, right? Because we have lots of different noise transients, lots of glitches. This code's really good at picking them up. It's exactly the same code we used to subtract that glitch that hit the binary neutron star merger. So if we only had one detector, we couldn't say. Unfortunately, we only have like 2.5 detectors right now. And so we ideally would have, 4 or 5 comparable sensitivity detectors all around the world, right? And then we'd be much more confident that we were seeing gravitational waves versus. So for this, Bayes wave's a Bayesian like follow-up code. The detection codes like coherent wave burst, they have much higher backgrounds than the template-based searches, right? Because they have to, because they're much more general, they can't reach the same sensitivities. So, but I think actually I was talking to Sergei Klemenko the other day. He was the person who first sort of came up with coherent wave burst. And I think he said something like, and this includes the latest 04 run, I think he said that coherent wave burst has picked up something like 70 or 80% of all LIGO events. So even if we didn't have templates, we would have gotten, a good fraction of all the LIGO events. But we wouldn't have been able to do the same physics with them, right? Because we wouldn't have known about the masses or the spins or anything like that. But you can maybe tease out some stuff from just the time frequency evolution of these things, but you really want the models to be able to do the most physics. But you also want to be able to detect something completely new. Like what if something came in that no one had thought of? We want to have a way to detect it, and then we could go and do the detective game of like, what is that, right? Yeah, and as I mentioned, in template-based analysis, you actually integrate out over the actual individual time or frequency samples, you integrate those out. And so it's a hierarchical Bayesian inference. And then that converts this, the marginal likelihood now is actually, now you end up with a posterior distribution on the parameters rather than like in Bayes wave, you actually get a posterior distribution for the waveform. But this actually maps it to a posterior distribution on the source parameters, which is what you kind of want to do if you want to do astrophysics. So for example, if you have, something like a signal coming in like GW15 and 14, and you need a model not only of the waveform, but also how it projects onto your detector network, but that's pretty easy to figure out, right? So you've got your gravitational wave coming in here, you got your two detectors, there's the signal as it appears in Hanford, there's the signal as it appears in Livingston. This time delay of about 7 milliseconds, a phase shift of about 2.9 radians, and about a 1.24 amplitude radio. And that's just from where it was on the sky, right? So all of these things give you the sky location and the polarization. And then as far as like figuring out the rest of it, this is where we use techniques like the nested sampling or Markov chain Monte Carlo to actually map out the spins and the masses. Stochastic backgrounds, you might think that they're different. I always thought they were different. I read Bruce's papers and there was Aina Flanagan and Bruce Allen and then Joe Romano back in the day. And it always looked to me like somehow everything else in gravitational wave astronomy was a likelihood, just the Gaussian likelihood data minus signal. And then there was a prior, and then there were stochastic backgrounds that looked completely different. And so I was chatting with Joe about this back in 2012, and I said, well, why do they look so different? I mean, so then we got thinking about it. Stochastic background is just another template, just happens to have coefficients that come from a random process. And so if you integrate those out, so this is the prior on the coefficients of the Fourier coefficients in this case, if you just integrate those out, because you don't really care about them necessarily, then you end up with this likelihood where H now stands for any other gravitational wave signal. So this is not just the stochastic, but this might be any other gravitational wave signals in there, like individual binaries. But now your likelihood function has a G in it instead of just a noise. So it's a combination. This is the I's and J's now are different detectors, and these are different frequencies. The I's and J's now are which detector. And so you get the term here, which is just the, assuming the noise isn't correlated between the detectors, it's a Kronecker IJ because the noise isn't correlated between detectors, but the signal is. And this correlation function you get just by integrating that out. In the LIGO language, it's called the overlap reduction function. In the PTA language, it's the Hellings-Downs correlation curve. And so it's just a stochastic template, but if you integrate out over the coefficients of the Fourier basis, you just integrate those out and get the marginal likelihood. What appears then, it puts it into the denominator. So, basically subtraction's equal to division. So if you marginalize over them, it becomes division, but you can also just directly subtract them out. And it's exactly the same. So you can actually model backgrounds like that. So for example, you can, if you just subtract sinusoids off, now they don't look like sinusoids because we also have a timing model and we're adding them up to a few different sinusoids, but you can actually subtract off the, you can do the pulsar timing analysis just by subtracting away a realization of the background, right? And so we use this in our analyses. So you actually model and subtract out the stochastic background and the data, of course, is a realization of a random process. So the data are not random. The data are an actual, they're just made up of sines and cosines, and we just model them. So if you integrate it out, which is what's normally done, you get these distributions for the amplitude and spectral index. But if you actually just model it as sines and cosines, subtract them off, and then you could just recover the parameters from a hypermodel, you get exactly the same result. So we're actually doing my group along with a group at Vanderbilt, we're actually switching all of the pulsar timing analyses to subtraction, not division. And why do we do that? Because if you divide, if you put it into the noise correlation matrix, that has a term that couples all the pulsars together. So you get a very large noise correlation matrix. This keeps it separate per pulsar. So we can do the analysis per pulsar, and we just subtract off the background completely and do it that way. And so it means we don't have any matrix inversions to do, because we actually subtract off all the red noise as well the same way. So our noise correlation matrix becomes diagonal. And so we're back to inverting a diagonal matrix, which is really fast. I really should have sort of emphasized this a bit more. In practice, especially with the bigger data sets, the main limitation we have is computational cost. And in the case of LIGO analyses and parameter estimation, it's just the evaluations of the likelihoods. And that's where fast techniques like heterodyning or moving to time frequency really speed things up. And in the case of pulsar timing, what slows it down is matrix inversions, but we actually just do subtraction, and then there's no matrix inversions, or they're diagonal matrices. So that makes it very fast. So we've got codes now that can analyze the 15 or 20-year data sets in just minutes with no matrix, just trivial matrix operations, and it's purely subtraction. We just model. Now, a lot of people don't like doing that because we're modeling tens of thousands of parameters at once, right? So our MCMCs have got tens of thousands of parameters in them. But we're used to doing that. In LISA, we do it with hundreds of thousands of parameters. Bayes wave running on LIGO has thousands, tens of thousands of parameters. And so we're quite happy to work with models with large numbers of parameters. And I don't like inverting matrices. So I much prefer just subtract off all the sines and cosines and do it that way. Much faster. Yeah, so this Bayesian approach all seems pretty simple, right? We just have to map out this posterior distribution and, for a single source, maybe 17 dimensions, and then we've got a whole bunch of sources. How hard can that be? I mean, these likelihood functions can be very multimodal. This one's a bit extreme. There can be a lot of expense in these waveform generation or likelihood evaluations, so you want to come up with sneaky ways of doing that. In the case of LIGO and Virgo, we got a whole lot of noise and the occasional signal. They're getting more frequent these days. In LISA, we have a relatively small data set, but there's millions of overlapping signals to deal with. And in PTA, we've got unevenly sampled data with different noise at every sample and complicated noise properties. So each one of them has their own challenges. One of the things that we can do to accelerate the analysis is you actually sort of fold in like maximum likelihood type techniques, frequentist type techniques to like perform a search to kind of get you going, and then follow up with a more expensive Bayesian analysis. So that's what most of these analyses end up looking like. For example, the LIGO Virgo analyses, all the online analyses are all frequentist, right? They're all done some variant of something like a maximum likelihood type search. And then, I'll talk now a little bit about how the sausage is made, where you feed in your prior and your likelihood, in this case with an MCMC sausage maker, and out comes your posterior and your evidence, right? But there are some interesting things that happen inside the sausage making. So I'm going to talk a little bit about that. As Teja told you about last week, one of the, standard approaches is this Markov chain Monte Carlo. So I think he said something about bunnies hopping across a field, something like that. Okay, well, it's bunnies hopping from X to Y here with some transition probability. And so basically it's like always go up, sometimes come down. And you've got your prior, your likelihood, and then your proposal. And this is how you propose to jump from X to Y or back from Y to X, right? And these are really key because if you don't have good proposals, you don't move efficiently. Your bunnies don't hop very well, right? So you want to hop around efficiently. So it's really key to the sampling is that you have good proposals. So when you're doing one of these analysis, there's a part that we call burn-in, which is like mapping out the dominant modes of the posterior. And then you've got to mix, you've got to explore them and map out that structure. Now, if you happen to know what the posterior distribution was, right? So if you knew the answer, you could use it as the proposal, right? So if you already knew the answer to what the distribution was that you're seeking, if you use that as proposal, then you pop that into the Metropolis-Hastings ratio and you get an acceptance rate of 1. So if you already knew how to draw from the posterior, you would get perfect sampling, right? The problem is you don't have that, but the better your proposal is, the better your proposal approximates the posterior distribution, the more efficient your sampling is going to be. And in the limit that it exactly matches the target, then you're going to get perfect sampling. There's some neat things. Here's a web page. I'm going to go a couple. Why is it not running? This is just illustrating the basic random walk Metropolis-Hastings exploration of a banana shape. And it's collecting samples, and you form up these histograms. And here it's just like taking random Gaussian jumps. The green means it was accepted, red means it wasn't. And just kind of repeating this process over and over, you eventually map out this distribution. But this sort of random walk Metropolis-Hastings is not very efficient, right? So we tend not to use it in practice, even though it's the simplest thing you could code up for a first. And here's an example of what you get. If you do this you end up with these distributions for mass ratio, precession, the chi effective, the chi precession, the masses, that sort of thing. So that's how it was done. I got a little. I've got an undergraduate, Piper, working with me along with my graduate students, Aidan Gunderson, and they've made this. We're about to put it up on GWAS, the Gravitational Wave Open Science Center. It's a little Python notebook, and it illustrates how the analysis works. I can't run it on my laptop because my Python packages, I don't use Python very much, mine are all screwed up. So I had Aidan make a little movie I could just play, but it's kind of fun. What you do is you grab the sliders, and this is for GW59, you can choose which events, and you move them around. You can see as you try out different parameters, right? You can fit the signal better. It actually shows you the signal to noise you're getting there as you move those things around. You can switch which parameterization you use and then move stuff around. Under the hood, the code's maximizing over the time, the amplitude and the phase for you, right? So it's correcting all those parameters. But essentially, this is what's happening inside an MCMC. But instead of pulling the sliders around the machine, is moving those sliders around and sort of trying out different values. But it's kind of fun. You can actually go and find signals this way. So we're going to have this up as a little game you can go and play to mess around with and you can actually, you don't have to pick from this list. You can load in new events if you want, and it will process them all for you. And it's amazing. It's a Python code that just runs in real time, right? So you just pull in the sliders, and it keeps up with what you're doing. So yeah, so Piper and Aidan have done a nice job with this little visualization tool. It's essentially what the computer does. One recipe that I've used over the years, so here's a recipe card for the methods we like to use. We use a combination of like local posterior approximations. So that's things like Fisher matrix approximations to the posterior distribution. We use these global likelihood maps. So things that kind of find all the different peaks of the posterior. We like to use differential evolution and parallel tempering. We mix all these together. It's always a good idea. Each one of them has its advantages and disadvantages. So you just throw them all in there. Then you got to do things, check that you recover the prior. If you set the likelihood to a constant, make sure you get diagonal p plots. I'm not going to go into those. And it's cooked once your distributions are stationary. Okay, so that's the recipe. Some of the ingredients here. This is the K here is the negative. It's the negative Hessian. So the Hessian of second derivatives of the log posterior is what we're taking here, right? So two derivatives of the posterior distribution, and we call it the augmented Fisher matrix, and we use those for local jumps. And then we use global likelihood maps, so that we have all sorts of maximum likelihood type stages to actually find all the peaks in the posterior, because MCMCs aren't great at finding peaks. So we use all sorts of hill climbers and things like that. There's actually a lot of work that's been coming. I'll get to that in just a second. In the machine learning community, I mean, under the hood of most machine learning algorithms, including all those large language models people talk to these days, you have some kind of a loss function, right, which essentially plays the role of like our likelihood, and you need to minimize or maximize it, right? And so it's just and it has many, many parameters. So what you have is a very large scale maximization problem. And so they use essentially various kinds of gradient descent type codes, which has then lent to the development of a lot of good global optimizers. And one thing we haven't done yet is build in a whole lot of that machine learning type techniques into this. These are all machine learning things, but they're old ones. I'm talking about some of the modern ones taken directly from the machine learning models to do this like overall mapping. But a lot of what we do is more like uses domain knowledge to make these things efficient rather than just a general algorithm. But I think we could learn a lot from the AI world on how to do these pilot searches. So for example, in Bayes wave, it's pretty simple to figure out what makes a good proposal. These are different quality factors of the wavelet, which a quality factor is the number of cycles. These are Gaussian envelope sinusoids. Q is the number of cycles that the wave executes before it damps down to sort of nothing, right? So Q of 4, 8, 16 here. These are just different maps of some LIGO data. And since the code is actually going to be dropping down wavelets, well, a great proposal is just to wavelet transform the data, and then you turn this into a probability map and say, you know what, it's probably not a bad idea to drop down wavelets here, because that's where the power is, right? Where these particular Qs and whatever. So this is the proposal that the Bayes wave uses under the hood, the main proposal that drives it. There's many types of population type MCMCs out there. There's an EMC. So we use in that case like a whole swarm of bunnies hopping around. And then from what the different bunnies are finding, you can kind of figure out the map of the overall shape of the distribution. Similar to that is differential evolution, where you take past samples and you use that to actually say, okay, if I have a past sample here, then you actually propose jumps along the directions between previous samples. And these are very effective at finding correlations and following them. So we always add that into our mix of proposals. Another big one is parallel tempering. If you need to get between different modes in your likelihood, the MCMC, it will go downhill, but doesn't really like, and it can't get through this pit of despair here. So to get to the secondary mode with parallel tempering, what you do is you artificially raise your likelihood to 1 over a temperature. And this all comes from statistical mechanics reasoning. And then your likelihood function looks like this. So it's much easier to get from the primary mode to the secondary mode because you've made it a lot softer. So we have walkers, bunnies hopping around at different temperatures, and the hot bunnies, they have a very soft surface that they're hopping around, so they can find the different peaks, right? And you can also use this to calculate the model evidence. So that's another bonus of this method. And so The trouble is the very hot ones tend to like lose contact with the good spots. So there's an exchange of information between the hot chains and the cold ones. So the cold chains remember the peaks, they get stuck there, whereas the hot ones move around, but because they're talking to each other, they communicate that information about the global structure. So the very hot chains explore the prior, the cold chains lock in on the peaks of the posterior. So that's a standard technique we use in all of our analyses. I'm not going to go through, there's a theory behind how you space the chains, and actually I have a paper that hasn't come out on this that explains how to do this in general, and this is for Gaussians, but we can actually do it for any distribution, but we haven't finished writing that up yet. I made this little movie years ago with another undergrad. Here's just Hamiltonian Monte Carlo. This is a map of some of the mountains around where I live, and you can see that with a Metropolis Hastings sort of like, it just crawls around, it kind of gets stuck. The highest mountain in this distribution, in this topographical map here, is right over here, but you know, with these little walkers, it's not going to get down that valley and go back up to that one. But then when you run it with parallel tempering, the white now are the hot chains, the black are the cold chain, and you see the swaps meant that the hot chain found the highest mountain. And so that's communicating its way around. So parallel tempering allows you to map out all the peaks in your mountain range, not just get stuck on one of them. Something else I've started using recently is Hamiltonian Monte Carlo. It's really cool. You write down a Hamiltonian, you got a kinetic energy term, you got a potential term. The potential is just the log posterior, negative log posterior. So this is what you're trying to map out. So you actually turn the process of doing an MCMC into mapping out a potential function, right? The kinetic term, use the Fisher matrix because that scales the jumps nicely. So that's called guided Hamiltonian sampling. So you use the Fisher matrix, which is the second derivatives of the potential. Does everyone remember normal modes from their mechanics class? Yeah, look at it. It's the second derivatives. You got that. I mean, it's just normal modes, right? So then you've got the evolution of the, so this P is the momentum, it's just an auxiliary variable using to move around, and the Q's are the actual parameters of your model that you actually really want to explore. And so you just evolve under Hamiltonian flows and you arrive at a new state, but because it's energy conserving, the acceptance probability is 1, right? So you get perfect acceptance because you're using a Hamiltonian. It's a symplectic manifold, so you're preserving energy and you just move around and you get perfect acceptance. Why doesn't everyone use this, right? It sounds great. Well, the problem is you have to calculate second derivatives of the potential and first derivatives, so you need first and second derivatives. Often the cost of calculating those derivatives is as high as just doing a likelihood evaluation, so you might as well just do crappier MCMCs and just use your likelihood evaluations to move things around. But these days, well, I haven't got to that. Here's another one of those movies from the same website. Here's showing one of these trajectories, and there's the jump. And so you can do these big jumps. There's the trajectory, the jump, trajectory. That's the Hamiltonian. Yeah, and off it goes. So you can really move well around. Notice how it's mapping out this whole distribution really well. But the cost is all of these evaluations. So I never used this before because all of these derivatives. But for the machine learning needed these efficient gradient-based optimizers for their loss functions for training AI. And so this led to automatic differentiation. And it's basically the chain rule. And the way to think about it is any calculation that happens inside a computer is just a nested collection of very simple operations like add, subtract, divide, maybe calculate a log or a sine or a cosine, right? And what you do is you essentially just overload each one of these operations and you carry around its value and its derivative, or maybe its second derivative. So it works for higher derivatives. It's just simplest to go through the derivation for first derivatives. I'm skipping the whole bit on the Clifford algebra that you can use to do this because I don't want to get completely QFT. I know that would get Bruce excited, but the rest of you probably fall asleep. It's faster and more stable than numerical finite difference, and if you did symbolic differentiation, you get this exponential growth in the chain rule, right? But because with automatic differentiation, it's sort of happening term by term. It doesn't exponentially proliferate, so it kind of keeps nice and small. Just give a really simple example. Suppose I have a function of two variables, happens to involve a product, sum, a difference, and a log. To a computer, it's made up of these primal functions. Well, first of all, it's just the entry variables x and y. Then you've got the product of the primals v0 and 1. Then you have the log of v0. Then v4 is the sum of v1 and v2. v5 is the difference between v4 and v3. And the final answer is v5. And so it's just sums, differences, and logs. We just need, suppose we want to know the derivative of this with respect to x. You can do the same thing. You just need these primal gradients. And the computer just knows, it just knows what the derivative of a sum is. It knows what the derivative, you teach it, what the derivative of a difference is, the derivative of a product or an inverse is, and just has those stored. Derivative of a log it knows as well. So it computes these. And with this, you actually end up then with the derivative, and it gets calculated, just gets carried along with the other part. So it's calculating the function and its derivative at just twice the cost for first derivatives than just calculating the function, right? And it's correct to machine precision, right? So you don't have the same error growth. And this is huge. This is why you have ChatGPT, unfortunately. It's this automatic differentiation is absolutely key. And we should be using more of this. Anyway, you can code it up for yourself. I don't know why my E went funny. It's really easy in an object-oriented language like C++. You can do it in any language. In Python, it's implemented in JAX and PyTorch and this sort of thing. So you can go and, I prefer to code these things up for myself so I understand them, but you can get off-the-shelf versions of this. So JAX is an entire language that's kind of designed to do this, and PyTorch has it all built in too. So this is really key, and makes Hamiltonian Monte Carlo actually viable as a technique. Yeah, I'm going slow. So I've already mentioned Bayes wave a bit. This is where we do the detection without templates. What I really want to introduce here, we also got to model all of these. You have to model the noise. And we do that various different ways. We need to model all of these noise transients. This has died. That's okay. So we model those, model the signals. But all of this, now we're talking models with huge numbers of parameters, right? So how do you deal with that? So we have a motto, model everything and let the data sort it out, which is sort of based off this quote in Latin, which basically is kill them all, for the Lord knoweth them that it his, right? That was when they were about to attack this town. They were like, well, how do we know the Catholics from? It's like, just kill them all. Anyway, here's an example. It's a little less bloody. Suppose we wanted to model this data set. We have 32 points. Let's model it with a degree. Here's the chi-squared, just to be frequentist, and then a chi-squared per degree of freedom. If I model that using a Legendre polynomials up to degree 32, I get a perfect fit. Chi-squared is 0, right? But the reduced chi-squared is infinite. So it's overfit the data, right? If I use 24, you can tell by eye, still overfitting, right? You go down to 16, doesn't look too bad. 8 looks pretty good. Anyway, if you go down to 4, you've kind of not got enough parameters in the model, right? So how do you know how many parameters? How many wavelets should I use? How many white dwarf binaries should I throw into my Lisa fit? We'll let the data figure it out. And the way we do that is we make the model dimension a parameter along with the model parameters like, so our Legendre polynomials here, they have they just have an amplitude, right? They just have a number, a multiplier times each Legendre polynomial. So they're one parameter per Legendre polynomial. And then we allow the number of Legendre polynomials to vary. So it varied and it preferred 7. Didn't mind 8. Didn't really like 6 at all. 9 was okay, 10 was okay. And these are just draws from, but this is now going to be marginalized both over the parameters of Legendre, which is the height, but also the number of Legendres. And it figured out for itself exactly how many to use, right? There was no penalty functions. It was just Bayesian evidence that was deciding it. So this is what we use. This is myself and Tyson in front of the Monte Carlo casino, because you got to do that if you do a lot of Markov chain Monte Carlo. And in the case of if you want to calculate Bayes factors, which are those evidence ratios, it's just by counting the number of iterations in model I and model J. Yes?
Is that you can go between the number of dimensions?
Yes.
Without any penalty cost. But like, we saw that you can, like, there is a decision criteria. So no.
Oh yeah, yeah. No, it pays an Occam penalty, the complexity of the model, right? So it's going to choose the simplest model it can that is able to, because as you saw with a very high dimensional model, if you get a perfect fit to the data, but you kind of overfitting the data. So you're paying a penalty. Basically, the prior volume gets larger, and when you actually look at when you calculate the evidence for those different models, you're paying a penalty from that larger prior volume, right? So it automatically is looking for a simple model, but not too simple. Yeah. So you don't add that penalty factor. It's just naturally there because it's using, what it's doing. It's comparing all these models, and it's calculating the Bayesian evidence between all these models, right? And that's how it decides. So it's selecting the models that have the highest evidence. Yeah, so you don't have to put in a penalty factor by hand or anything like that. Yeah, so this is what we do. We have, and the models, they don't even have to be, they can be completely unrelated, right? You just throw in just different components that aren't in any way related. This is an old simulation from back in S5 showing Bayes wave back then. And modeling, there's a data with a monstrous great glitch, and then we ate up the glitch, and then we can model the power spectrum and everything. So that's ancient paper. Yes.
So in this transdimensional one, do you need to introduce proposals that
Yes.
go from one space?
That's
to
right. Yes.
others?
Yes.
Is this easy or hard to do?
That's a little hard. That's kind of the key to it all, right? The proposals are always the key. And that's why we have these global proposals are really like these pre-maps that we make of the data. So we always have an overall, we need to know, the overall structure. We need to have mapped out to some degree our likelihood surface so that we can make good jumps. And this is now jumps in model space as well. So
Every some model that has a fixed dimension in some way, and then make proposals and connect.
That's right. But you can do it sort of, you don't have to do it jointly, right? So you can get away with sort of modeling different components separately there to a fair degree. So it doesn't have to be the full joint solution for that map. Because remember, there's proposals. They don't have to be perfect. They just have to be close-ish. Closer the better. Yeah, so what have I also got? Yeah, forget that. Yeah, so more recently, we've been doing this. This is my final slides. Jointly modeling signals and glitches in LIGO data. And you see that if there were some of the LIGO events where people had made claims of like precession or claims of very high mass ratios, but it was in data that was beset by glitches. And when you actually model the glitches simultaneously with a gravitational wave signal, all the evidence for these more exotic type things went away. So it was just dirty data, not actually a more exotic object that we were seeing. So I think it's important that we model all of these. And I think I'll stop there and take a couple of questions. Yes.
So my question is like the wavelets basis and the Fourier basis are just different sets of complete orthonormal basis. So why does wavelet basis work so well comparing to Fourier basis?
Yeah, so I should clarify first, there's different kinds of wavelets. The ones that I was talking about with Bayes wave are continuous wavelets. They're not orthogonal. So they form a frame, not a basis, right? The ones that I was talking about for evaluating the likelihoods in as an alternative, those are orthogonal wavelets, like you say. So that is just a, it corresponds just to an orthogonal transformation of the data, right? So the information's identical. So there's no difference. It's the same thing between, or at least in principle, a Fourier transform, right, of the data is identical information to the original time domain data. Same goes with if you forget about windows and details. The same goes for the wavelets, right? So the discrete wavelet transformation is lossless. It has exactly the same information. It's just a repackaging of exactly the same information. But just think for a minute about the packaging of the information in the time domain versus the frequency domain. Like, why do we look at the frequency domain? Well, frequency, the frequency content of a signal is something that we relate to and can kind of understand. So it's a representation that makes a lot of physical sense to us, right? And a lot of signals are way more compactly represented. For example, if it was something that was close to being a continuous wave, for example, it's very compactly represented in the Fourier domain, whereas it's very spread out in the time domain. So each of these domains can and time frequency is sort of a nice in between, but it's exactly the same information. You should get exactly the same your likelihood should return the same number, whether you're calculating it in the time domain, frequency domain, but you just have to calculate your correlation matrix in each one, right? And if you're in a representation where the correlation matrix is as close to diagonal as you can get it, the computational cost is going to be lower because there are efficient computational techniques for inverting near diagonal matrices, for example. So another way of handling non-stationary noise is you just include the off-diagonal elements in your Fourier basis and model those, and then hope that it's diagonal dominant because it's almost stationary, and then you can do it that way, right? But it's just the information's no different. It's just a packaging, and some packagings are more convenient than others. And the signals in time frequency are, since gravitational wave signals tend to come in harmonics, they're just nice tracks in that space. So they can be compressed. It's all about compression, really. Look at them both. Bruce.
You said something I didn't know, and it's interesting to me, which is that you said that you and Vanderbilt are actually doing PTA analysis not by sort of inverting huge correlation matrices, but instead by subtracting sort of.
Yes.
Can you say a little bit more about that? Just trying to explain to me what it is, because I didn't know you were doing something different that way.
Yeah.
Can you just?
I mean, okay, yeah. So I don't know if I need slides for it, but I'll go back to an equation just so I have something to point at. Yeah, is that the right one? Yeah. Oh, yeah, the slide that was next of actually showing it in practice. But before we get there, so the derivation that takes you from representing it as just the usual likelihood data minus model, right? Since the model is given by this Gaussian, which I've given in the frequency domain there, rather than so the model would be, in this case, the various Fourier coefficients, but you don't really care necessarily about the exact values of those Fourier coefficients. So because it's Gaussians and it's a product of Gaussians, it's a, what do you call them, conjugate prior. You can actually just integrate it out, right? And I mean, lots of people have done this. The papers, there was the one that Joe and I did it, and Lentati et al. Did it in this paper, but it's been done in lots of other fields many other times. Yeah, that shows up once you do the integration out, right? But there we analytically integrated out the Fourier coefficients. And then the result you get is that you now, instead of just the noise correlation matrix, you end up with this on the denominator, right?
That's kind of a standard thing now.
Yes, right. And then you're doing, instead of analytically, and it seems crazy, like why would you, if you can analytically integrate something, and there's a lot of Fourier coefficients, right? So you say, we don't really care about their particular values because that's just some realization of a stochastic process. We just care about its power law or whatever, right? We just care about the spectrum. So why would you not just, if you can do it analytically, why the hell would you do it numerically? We're just doing that integral numerically, right? So instead of analytically integrating over the A's, we numerically integrate over them using a Markov chain. And that might seem stupid, but what we're trading off is if we did it analytically, we end up with matrices that we have to deal with. We model both the red noise and the gravitational wave background. All our matrices are just white noise now.
Using a large number of parameters is all you have to do for all the different coordinates.
That's right. That's right. For every pulsar, we have a huge number of parameters.
Just throw this into your
Yes.
MCMC meet grind.
And it just grinds it. But we're using very, very efficient samplers, right? So if you used a random walk Metropolis Hastings, the scaling goes something like n squared with a number of parameters. We're using samplers that scale as n or very close to it. So that way we beat the matrix inversion cost. Yeah. Yes.
So in the very last slide, one of the slides, so that you model the glitch and the signal at the same time.
That's right.
And then you say that, well, I agree with the logic that if I had to by hand analyze the thing and so, and the entire community would say, Jonathan, all the computers are down, you have to do it right now, then I would try to remove the glitch myself and find a good one. But how do we trust the computer to do it when it has to consider the entire parameter space and what is the parameter, like what is the phase? How is it done like this?
Yeah, we're mostly relying on the fact that, again, we have multiple detectors, right? So the signals are across the network. The glitches are hopefully separate and in, different detectors and independent. So we're really using the fact that we've got multiple detectors plus we're using this with a model, we're using it with template-based models for the signals. So that also locks you into a much smaller possible range of things. But you really need to do these things simultaneously because the glitch model, like if you leave the glitch in there, you bias the analysis. If you remove the glitch incorrectly, you bias the analysis. You really need to do both simultaneously so you don't, you don't want the glitch, the model for the glitch to eat up part of your signal and vice versa, right? So you have to do a joint modeling. I've shown a couple of people this. I don't want that. I'm going to stop sharing and then I want to share something else. So related, if I can find it. Sorry, this is just was a bad idea. Now I can't find what I want to show you guys. It's really cool though. You can't see anything I'm doing right now, right? I can't find it anywhere. That's annoying. Yeah, so we've now started to, showing you the modeling of the lines, of the glitches and everything. and then of the spectrum. I'll show you this.
Daniel, you might not realize it, you're starting to cut into the coffee.
Okay, I should stop.
Well, I'm not sure yet, so, but just FYI.
Okay, one last, I've got a thing to show you and you can all leave. Where did Zoom go? So now, instead of modeling the power spectral density as having lines and, and smooth components, we actually coherently subtract all the lines. So this is some dirty Virgo data from back in 02. It's about as bad as it gets. Hundreds and hundreds and hundreds of lines, all gone. So we just subtract all the lines in LIGO and Virgo now. But you want to do that at the same time as modeling the signals because you don't want your line removal to eat your signal, right? So you do it simultaneously. Anyway, so glitches are gone, lines are gone. Just model it all. All right, go and have some coffee. Thank you.